Log on, tune in, find out. Another good idea from Cambridge.
To introduce the first speaker of this afternoon, Dan Segal from Oxford, who will speak about CFSG and proof theory.
Well, I was very flattered and a bit nervous to be invited to speak to this group, because for most of my professional life I was rather terrified of finite simple groups, and I thought they were far too difficult, so I tried to avoid them. But about 15 years ago, I started collaborating with various people who actually were quite comfortable with finite simple groups, and they showed me that this is a very useful thing to know about. Even if you can't contribute much to the classification program, you can very well use it. So I thought I'd talk about a couple of topics today where, perhaps in a slightly surprising way, knowing about the classification of finite simple groups has turned out to be quite useful in tackling problems which, on the face of it, don't have anything to do with simple groups, or not very much to do with finite groups. I wrote down a quote from Martin Liebeck, who I think just arrived. I saw him. There's this very big book called The Princeton Companion to Mathematics. I don't know if people have been looking at this, which I found very enjoyable, browsing through it. But I think that the choice of subject rather reflects the prejudices of the editor. There's very little group theory in it. There's nothing about algebraic groups, very little about finite groups. And I think there's 2 pages about the classification of finite simple groups out of over 1,000. And the article about finite simple groups was written by Martin Liebeck. And the quote I wrote down from him says, "One can now solve many problems in a concrete way by reducing them to the now known list of simple groups, rather than abstractly by deducing them from the axioms for groups." So when I saw that, I thought, well, I'll illustrate this with a couple of topics. And I apologize to people who've heard all or some of this before. I hope not everybody has heard everything before. So the first topic is about groups with polynomial subgroup growth. So this is about infinite groups, infinite finitely generated groups. And usually there's not much you can say about infinite groups in general, but one thing you'd like to do is to somehow separate them out into ones which are straightforward and ones which are complicated, or ones which are large and ones which are not so large. And one fairly crude way to do that is to just say, how many subgroups do they have? So if G is a group, you can consider this numerical function Sn of G to be the number of subgroups of G whose index is at most n. And then you can ask, what does the growth of this function for a given G as a function of n tell us about the group G? So, first of all, you can look at some straightforward examples and say, well, what is it for groups that we know about? Well, let's say F sub D is the free group on D generators. Then, actually the formula I've got is, there's an exact formula for the number of subgroups of index n due to Marshall Hall from 1949. But if I'm only interested in the growth rate, I'll just give a rough formula. I'll say Sn, suppose D is at least 2, so it's a non-abelian free group. And Sn of Fd is about n times n factorial to the d minus 1. So in some rough sense, it grows about as fast as n to the n. So it's a bit faster than an exponential function of n. So it has a lot of subgroups of small index. And of course, any degenerator group will be a quotient of this one. So this will be an upper bound for the growth rate of subgroups in degenerator groups. So this is kind of the top end. At the other end, of course, if you take a free group of rank 1, an infinite cyclic group, it has just one subgroup of each index. So here you have a sort of dichotomy, a very super exponential function and a linear function. Give you the sort of the two ends. And so the question is it sensible to say that if groups have subgroup growth rather like that, they're going to be rather like free groups, and if they have subgroup growth rather like that, they're going to be rather like the integers? This is a crude kind of measure. So let me give you a nice result which shows that this kind of question is actually can be quite sensible, can give you interesting results. So here's a theorem which is due to Alex Lubotsky. So let gamma be an arithmetic group. I will say a nice-ish arithmetic group. There are lots of bits of definition which I don't want to bore you with about simply connected semi-simple algebraic groups. But that's where this arithmetic group will be living, a nice-ish arithmetic group. And what you want to count is not all the subgroups of finite index, but the congruence subgroups. These are the ones which are defined simply in terms of the arithmetic. These are subgroups which contain the kernel. If you have natural maps from gamma into gln z over mz. Oh, sorry about this corner. For every positive integer m. And the kernel of one of these maps is called a principal congruence subgroup. So the congruence subgroups are the ones which contain those kernels. So they're the ones which you can see just from the arithmetic of the ring. So if gamma is a nice-ish arithmetic group with Cn gamma congruence subgroups of index at most n, so let gamma be. And what can we say about Cn of gamma? There exist positive constants a and b such that n to the a log n over log n is less than or equal to Cn of gamma, and it's less than or equal to something of the same kind with b to the log n over log n. So the congruence subgroups grow in this sort of slightly sublogarithmic way, n to the log n over log n, up to some power of that. So these are the subgroups which sort of occur naturally because of the arithmetic. But of course, these may not be all the subgroups of finite index. The congruence subgroup problem asks for which arithmetic groups do these exhaust the subgroups of finite index. Some arithmetic groups have the congruence subgroup property, some don't. If gamma has the congruence subgroup property, this is the same as Sn of gamma. If it doesn't, Sn of gamma might be bigger. Well, it is bigger by definition, but how much bigger? if gamma does not have the congruence subgroup property, then there exists epsilon positive such that Sn of gamma is bigger than n to the epsilon log n for all n, or all large n. So there's a big difference between this growth rate here. It's n to a constant times log n. Here it's n to a constant times log n divided by log n. So if there are non-congruent subgroups of finite index, there are very many more of them. So the growth rate, so if you forget about congruent subgroups now and say, what does subgroup growth tell you about the group? You can tell just from counting the subgroups of finite index if it's one of these nice arithmetic groups which has the congruent subgroup property or not. Because it has the congruent subgroup property if and only if the growth rate of subgroups of finite index is very much less than that. So I mention this because this shows that this crude counting function actually can indicate quite a lot about what's happening inside a group. Good. Right. So subgroup growth does give you some sort of distinction, certainly in the special case of these arithmetic groups. What about groups in general? So we now know something about free groups and arithmetic groups and the integers. So you have three kinds of growth we've discussed already. This super exponential kind, this logarithmic kind, two kinds of logarithmic growth, and this very slow kind. Right, so let me just summarize. For arithmetic groups, examples are SL2Z, which is virtually a free group, and here you have super exponential subgroup growth. Medium, arithmetic groups with CSP, congruent subgroup property. And then what about slow? What about the groups which are like Z? You see, these are, of course, these are basically things like SL3Z, higher rank arithmetic groups. They're quite nice in a group theoretic way, but they're obviously a lot more complicated than Z. I mean, they tend to be associated to simple groups, but they're very far from free groups. So what can we say about groups with very slow subgroup growth below this sort of level? Got it. Well, what other examples are there? Here's PSG polynomial subgroup growth. If there exists, did I give a name for it? Doesn't matter. Alpha such that Sn of G is less than n to the alpha, less than or equal to n to the alpha for all n. Right, so these are groups which are going to be, in terms of subgroup growth, less complicated than arithmetic groups, because the arithmetic groups have all these congruent subgroups, n to the log n over log n of them. So they might be rather like the additive group of integers. the infinite cyclic group. The question is, are they? So are there other examples? Well, there are some easy examples. So examples, let's say e.g. groups which are poly-Z, polycyclic groups, finitely many iterated extensions of cyclic groups, or more generally, poly, a subgroup of Q. So it's a group which is filtered by a chain of subgroups, and the quotients are subgroups of the additive group of rationals. So these are things like that. These are generally how we think of soluble groups of finite rank. So finite rank doesn't just mean finitely generated, it means that every finitely generated subgroup has a bounded number of generators. So these are groups like that, or slightly more generally. And because I'm interested in counting subgroups of finite index, I'll only think about residually finite groups. Because if you factor out the intersection of all the subgroups of finite index, you don't change the function Sn of G. So we better forget about it. So let's say among finitely generated residually finite groups, these, i.e. the soluble groups of finite rank, are just the soluble subgroups, the soluble linear groups over the rational numbers. You can sort of see why that is, at least, that the unipotent part will be filtered by things with additive groups of the rationals, and then if it's a finitely generated group, the torus piece on top will be a finitely generated abelian group. So finitely generated residually finite groups which are soluble of finite rank. So these are just the soluble Q linear groups. Okay, I'm taking some time introducing these because these are the easy examples of groups with polynomial subgroup growth. It's quite easy to see that, I mean, basically because of that, you just sort of iterate that and you end up with not necessarily linear subgroup growth, but at least polynomial. And now this rather surprising theorem, which was quite surprising to us. This was joint work with Alex Lubotsky and Avi Mann. And I think we published it in 1993. So I'm afraid it's quite old. That among finitely generated residually finite groups, the ones with polynomial subgroup growth are exactly these and no others. So a finitely generated residually finite group has polynomial subgroup growth if and only if it is virtually, we can't get away from, virtually means up to finite index, if and only if it is virtually soluble of finite rank. Okay, so that's a result which, on the face of it, it's about infinite groups. It mentions finite groups in the sense that we're talking about subgroups of finite index. And you might think, in some sense, simple groups will be involved because to show that a group is soluble, you've got to show it doesn't have any non-abelian simple pieces. But it's quite a long way from realizing that to seeing how you can actually get the finite simple groups into a question like this. So I thought I'd spend a few minutes just roughly sketching how one proves this, not with any details, but to sort of explain why we couldn't have done it without the classification of finite simple groups. Okay, so let me quickly sketch the main steps in the proof of this. In one direction, the if direction, as I said, is pretty straightforward. The interesting part is if you have this growth hypothesis, what does it tell you about the structure of the group? This is a purely a crude growth rate hypothesis. It's supposed to tell you that the group is soluble and has finite rank. Okay, so ideas. Maybe ideas is putting it too grandly. Steps in the proof of only if. So we'll assume G has polynomial subgroup growth. And my standing assumption is that it's finitely generated and residually finite. So what we often like to do in infinite group theory is you can't prove a theorem because you've got nothing to get your teeth into. So you say, let's prove it for linear groups. Because with linear groups, you've got things to work with, matrices. There's something to get hold of. So A, let's suppose that G is linear. It's a finitely generated linear group. So it can be represented by matrices over some nice finitely generated ring. And so then we start doing the usual sorts of reductions, which I won't give you a lot of details. So one, we do a specialization argument. But if we're going to do reductions, we better know what we're allowed to assume and what we're trying to prove. And let's try to prove that G is virtually soluble. Or solvable. Once you know it's virtually solvable, then there's a lot of machinery invented by people like Philip Hall for taking those groups to pieces. And then you show it has finite rank. And that's not so hard. Well, it's not trivial, but it's a different kind of question. The difficult thing is, and the interesting part is this solubility. So let's try to prove that G is virtually soluble. Okay, so if that's all we're trying to prove, then no. I shall not even say what I was going to say because it's too complicated. Let us take the first step. Specialization argument. So all we know is linear over some field. We'd like to get it linear over the rationals. So what's a specialization? Well, the group consists of matrices over some finitely generated ring. This finitely generated ring will have some transcendental elements. You specialize them down, and you end up with well, if you're in characteristic 0, you end up with matrices over some finite extension of the rationals. So you're reduced to the case where G can be embedded in GLDK, which in turn can be embedded in GLD dashed of Q, where K is some algebraic number field. So I won't worry about the other characteristic. Let's say, suppose that G is linear in characteristic 0. What I was saying about solubility is that if the group is not virtually soluble, it will have some image under one of these specializations which is not virtually soluble. That was the point of what I was trying to say. So we replace it by a non-virtually soluble image under a specialization. And if you end up getting a contradiction that way, you will have the contradiction you want. Okay, so we've got a linear group over the rationals now. Okay, once you've got that, and it's finitely generated, there's some wonderful arithmetical stuff called strong approximation. Which is these wonderful theorems due to Norrie and Weisweiler. And sort of adapted to the present purpose by Alex Lubotsky. And I think what's not well known is that he actually asked Weisweiler this question in order to solve this problem, or this kind of problem. So that was one of the origins of the Weisweiler strong approximation theorem, was Lubotsky wanted to apply it to group theoretic questions. So what does it tell you? It tells you if you have a finitely generated linear group over the rationals, then you look at its Zariski closure, it's some algebraic group. And then you look at the congruence images of the group you started with. That's going to be very similar to the congruence images of an arithmetic group in that algebraic group. So that's a bit vague, but it tells you that the let me just state it. If G is now a linear group over the rationals, okay? If G is not virtually soluble, then there exists the following. There exists an infinite S arithmetic group gamma, and it's an S arithmetic subgroup in some simple algebraic group. Defined over the rationals. I'm going to have to go on here, sorry. So we've got this arithmetic group gamma and this linear group G. And the point is that all the congruence quotients of gamma also occur as quotients of G, or at least up to finite index. So you have this very intractable sort of group generated by finitely many matrices. You don't know anything about what its images are going to be. But in fact, magically, you take its Zariski closure and you look at the images of the arithmetic group there, and you can see them already in the group you started with. If G is not virtually soluble, then its Zariski closure will have a semi-simple part, which is not trivial. That's where this is coming from. So what's the conclusion? So and a subgroup G naught, normal of finite index in G, such that every congruence quotient of gamma is a quotient of G naught. So that's the strong approximation part. Okay, there's a more elegant way of putting it, which I won't expand on, but for people who like this sort of thing, you look at the profinite completion of this subgroup G naught, and this maps onto the congruence completion of this arithmetic group. Okay, so why is this relevant? Well, we've assumed that our group has polynomial subgroup growth. So the number of subgroups of index n is bounded by n to the alpha. But the number of congruence subgroups in here is at least n to the log n over log n times a constant. Every congruence subgroup here corresponds, if you pull it back, corresponds to a subgroup of finite index n. There may be more. So what do we have? So Sn of G naught is greater than or equal to Cn of gamma, which is greater than or equal to n to the b log n over log n. And then it's a tiny step to deduce that Sn of G is not polynomially bounded. can't be. Okay, so I still haven't mentioned simple groups, except for a simple algebraic group. But, I mean, in the case of linear groups in characteristic 0, that finishes the problem. The group has to be soluble, virtually soluble. Or it would have all of these congruence images, and there'd be too many of them. Okay, so how do we know that the group is linear? This is the interesting part. I mean, it's another interesting part, a different part. I mean, when Lubotsky and Mann came up with this part for linear groups, it was exciting for me because I'd asked this question and no idea how you'd even start thinking about it. And then Lubotsky had this nice idea of getting Weisweiler to prove a strong approximation theorem. Okay, B. How do we make the group linear? Okay, so how do we know that G is linear? Okay, two lemmas. Take an alternating group on M things. Let's call it S. Then it contains a subgroup E, which is elementary abelian of rank R, elementary abelian 2 group of rank R, where R is greater than M over 4, if I've got it right. Okay, a not difficult exercise. Alternating groups have large elementary abelian subgroups. Take groups generated by disjoint involutions. Okay, lemma 2. Let S be Lm of Fp to the E. This is a group of Lie type, and Lie rank M over a field with P to the E elements. Then that contains an elementary abelian subgroup, which I'll call E of rank R for some prime P, where R is bigger than ME over 8. And we also want E to be quite big. E to the power 248 is at least the size of S. Okay, these are something like, this 248 comes from one of the exceptional groups, the dimension. It doesn't really matter. The point is we've got bounds like that. And in a group of Lie type, you get things like the top right-hand corner of unitriangular matrices will be a large elementary abelian P group, where P is the characteristic. Okay, so what does that tell you? That tells you, I don't want to spend much longer on this, but so I'll get to the point. The point is that the classification of finite simple groups tells you that they all look like that. There's no reason at all from the axioms of group theory, as Martin would say, to suppose that a finite simple group should have a large elementary abelian subgroup, large, which you can control its size in terms of its order. If this happens to be the case, because there aren't any other simple groups. It's one of these mysterious facts of mathematics. Okay, I won't write the details, so now consider elementary abelian. No, sorry, consider non-abelian chief factors of finite index in G. So here is our finitely generated infinite group with polynomial subgroup growth. Here's a pair of normal subgroups of finite index, and here's a simple group, or rather a product of copies of a simple group. That's a chief factor, right? I'm just going to wave my hands here. Using these little estimates and what we know about the automorphisms of finite simple groups like that, you can see that in here here you have E cross E cross E. It's a large elementary abelian piece. So, and this large elementary abelian piece is relatively large compared to the size of the simple groups it's sitting in, and also relatively large compared to the size of the automorphism group of this object, which we'll use to bound the index. The automorphism group of S, which is small, and L, the number of copies. So if we put all that data together, you find that there's a large elementary abelian section not too far from the top of the group. And now the key observation is that if you take an elementary abelian P group of rank R, has about P to the R squared over 4 subgroups of index about P to the R over 2. The number of vector spaces of about half the dimension is a constant times the square of the dimension. That's the point. Okay? And now so that means inside this elementary abelian piece there's lots of little subspaces, and because you've got a square there compared with the dimension, you play it off against all of these other parameters, and you find that basically this thing can't happen if the number is bounded polynomially in terms of the index. Or in other words, everything is bounded absolutely. So using SNG less than or equal to n to the alpha for all n implies L and R bounded in this picture. R is the rank. Everything's bounded actually. And mod S. So what CFSG tells you is that the simple groups occurring are the ones we know about. And so the moral is that there are only finitely many of them. Okay. Actually, that's not quite true. Mod S isn't bounded. Sorry. R is bounded. So conclude R is bounded. The rank, or n in case of alt n. So there's only finitely many alternating groups. And at first sight, there might be infinitely many simple groups, but they have bounded Lie rank. And now the final bit of the jigsaw is that, so we can forget about these. We may get loads of these, but the point is that these ranks are bounded. These m's, sorry. Well, the r's and the m bound each other. Okay, and these therefore have linear representations of bounded degree. So this is the essence of it. So the moral is that moral, let's put it this way, G over the centralizer in G of M embeds in GL K of FQ. So if M is any non-abelian chief factor. And here, K is bounded. The Q may not be. Right, okay. So now we're beginning to get close to a linear group of bounded degree, because we've got a bounded thing here. So then you finally look at G over the intersection of all of these things. And then there's one final ingredient, which is sort of like Maltsev's local theorem. Maltsev observed a long time ago that a group in which every finitely generated subgroup has a linear representation of degree k is itself a linear group of degree k. It's a first-order statement in logic. Okay. John Wilson observed that if you have a finitely generated group which maps into linear groups of degree k like this, then the group itself will be linear of some larger degree over some field or over some product of fields. But that's not a very difficult thing once you've observed it, but it's very important. So we could just say, so the third step is, if you like, Maltsev Wilson local theorem implies G modulo stuff is linear over C, actually. We need a bit more. The point is, each finite field each characteristic only comes finitely many times. One can check that, and then you end up with a field. So what's this stuff here? This stuff here is where there are no non-abelian chief factors at all. By the first part of the proof, this quotient is a virtually soluble group. The whole thing is residually finite, so the whole thing has to be virtually soluble. So that's how it works. Okay, so that's enough on the first half of the talk. I've spent 3/4 of doing it. But you see, the moral of the finite simple groups is that they have quite large abelian pieces and quite small linear representations. That's what one has to know. If you know that, then you can read off a lot of information about situations, infinite groups, where you have infinitely many of these things, but you have a bit of control. So that was that. So let me talk now about a completely different topic and a bit more recent. So this is about groups which are even more infinite. They're not finitely generated abstract groups, they're finitely generated profinite groups. Okay, let's pretend that this has nothing to do with finite groups at all. I won't write this up, but if somebody says, what's a profinite group? You say it's a compact, totally disconnected topological group, right? Nothing to do with finite groups. But of course, that's a bit of a cheat, because really a profinite group is a group which is an inverse limit of an inverse system of finite groups. And I think the most useful way of defining it is, so a profinite group, so let's call this, was that 1 or A? 1, I think, so 2. Profinite groups. So a profinite group is a compact Hausdorff, I suppose, topological group having a base of neighborhoods at the identity consisting of subgroups. And I'll say finite index subgroups. And I put finite index in brackets because in a compact group, any subgroup which contains an open set must actually be a subgroup of finite index. Right. So the topology is defined by this choice of a family of finite index subgroups. Right. So it's finitely generated. A profinite group is a compact Hausdorff topological group, G. So G is finitely generated if it's finitely generated in the category of topological groups. In other words, if it has a finitely generated subgroup in the ordinary sense, which is dense. If G has a finitely generated dense subgroup. Okay, so now here is something which I think is a bit surprising. But people who've heard me give talks recently won't be surprised, I'm afraid. But I see some unfamiliar faces. So here's a theorem. Okay, so let G and H be profinite groups. With G finitely generated. And let theta G to H be a group homomorphism. Homomorphism. Then theta is continuous. If you're an algebraist, you're used to doing algebra, all of this sounds okay, and then suddenly you think, where the hell did that come from? How does the algebra, all you're told is that this is a mapping which preserves the group operation. Why should it preserve the topology? Okay, well, it's an interesting theorem. It has all sorts of corollaries. So corollary, the topology on G is uniquely determined by its group structure. Because you could take H to be another copy of G with a different topology, and theta to be the identity map. And then and the identity map's continuous. It would be a continuous bijective homomorphism between Hausdorff groups that makes it a homeomorphism. So, why should that be true? Well, here's the reason why it's true. Well, the first hint of the reason. So, in a finitely generated profinite group, every subgroup of finite index is open. And it's really a 2-minute exercise to realize that those two things are equivalent. So let me just put it's equivalent. Right. So obviously this makes it clear that the topology is uniquely determined because you simply take all the finite index subgroups as a base for the neighborhoods of the identity. And even if you didn't know they were to start with, you do now. Why might this be true? Okay, suppose you want to prove it. You need some way of generating open subgroups just using algebra. And here's a first step. So, why? Suppose H is a subgroup of G, a finite index. Then, obviously, there's a normal subgroup of G, or finite index contained in H. The quotient is finite, so there's some number Q, some positive integer, such that G to the Q is contained in H. So that's a subgroup generated by Qth powers. Just generated in the algebraic sense. Okay. So if we could prove that this subgroup was open, it would follow that H was open, because anything which contains an open subgroup is open. Why should G to the Q be open? Well, let's look at what G to the Q is made of. So let's just consider the set of qth powers. And then what is G to the Q? It's the group generated by this set. So it's a union of all the sets where you take a product of n qth powers for some n. And I invented this notation GQ star n to separate it from the qth powers. So this means that this is a product of n things, each of which is a qth power. Right. Now what do we know about these sets? The map x goes to x, well, let's put it this way. The map x1, xn goes to product xi to the q from 1 to n. That's a map from n copies of G into G. It's a continuous map because we're in a topological group. Okay, it's continuous. This is a compact topological space, so the image is a compact thing, and therefore it's closed. So each of these sets is closed and compact. Okay. So now here's a fact. GQ itself is closed in G if and only if there exists n such that G to the Q is equal to G sub Q star n. In other words, if and only if this infinite tower actually stops at some finite stage. Okay? The only if, I mean, if this being closed implying that is an exercise for you. It's a topology exercise, the bare category theorem. Okay? We don't need it. All we need is the obvious fact that each of these sets is closed, as I've just said, because it's compact. So if the whole subgroup is equal to one of these sets, then the subgroup is closed. Okay, so at least if we want to show that this group is open, if it's open, it's certainly closed. That's one of those things in topological groups. Okay, so at least we need to show it's closed. How do we show it's closed? To show it's closed, it's equivalent to proving that, which is now a piece of algebra. So we've reduced something to algebra. This is a purely algebraic statement, that every product of qth powers is a product of n qth powers. Okay. Supposing we can prove that. So my time is running out, so let me just quickly say, right. Okay. Supposing we prove this statement. Supposing we prove exclamation mark, right? Then G to the Q is closed, and that implies that G to the Q is open, and that's because of the solution of the restricted Burnside problem. To say it's closed means it's an intersection of open normal subgroups. And the quotient by each of these open normal subgroups is a group of bounded exponent with a bounded number of generators. Therefore, they have bounded order. So these normal subgroups all have bounded index. If you intersect all of them, it stops after a while. So you actually get this being open. Okay? And that implies theorem 5, etc. Was it theorem 5? Theorem 4. As I said. Okay, so why should this be true? Or rather, why? Yeah, it's true because of star. And because my time is very short, I will write up a theorem, which doesn't seem to have anything to do with star, but is the reason why star is true. I don't mean star, I mean exclamation mark. So, first of all, this is a statement about a finitely generated profinite group. Okay? It's very easy to see, again, it's one of these exercises, that this holds for the profinite group G, if and only if it holds with the same n in all the finite quotient groups of G, the finite continuous quotient groups of G. So really this is, although as it stands it's a statement about topological groups, it's equivalent to a statement about finite groups with a bounded number of generators. So let me just state this. I'll state two theorems and then I'll stop. So I should say everything in this last part of the talk is due to Nikolai Nikolov. And me, Nikolov. So here's a theorem. There exists some function f such that in every D-generator finite group G, G to the Q is equal to G sub Q star F dQ. That's the short way of saying it. Every product of qth powers for any positive integers D and Q. Every product of qth powers is a product of boundedly many qth powers, where the bound depends only on the number of generators of the group, of the Q. Right? And why is it true? Uses. So to prove it, we argue, it's actually a very, very long roundabout proof, and we published two big papers in 1997 where we couldn't prove this. We proved this with another parameter in there. And then 2 months ago, I realized that actually it was just a small step using what we had proved to get rid of that parameter. So this is actually quite a new result. It's 2 months old. So it's a long, complicated reduction argument, which eventually reduces it to a question about finite simple groups. I should say, of course, Martin Liebeck, Jan Saxel proved this for finite simple groups. Sorry. Martin Liebeck and Aner Shalev proved a more general thing like this for any word in finite simple groups. That given any group word, there's a bound depending only on the word, such that every product of word values is a product of bounded length in any finite simple group. Before that, Jan Saxel and John Wilson proved exactly this statement, again for finite simple groups. Independently, Martinez and Zelmanov also proved it. Okay? Finite simple groups are all two-generator. So they didn't have this parameter in, but for finitely generated groups, in general, we need this parameter. Okay, however, it's not enough to use that fact about finite simple groups. This is the other moral is when you're trying to prove something using the classification, the thing you're trying to prove it's not enough to know that it's true for the simple groups. You end up asking a lot of other questions about simple groups. Okay, so let me just state this theorem, which is rather complicated, but I think it's the most general theorem of its kind. So, right. So let Q be a natural number. Then there exists natural numbers C and M with the following property. If S is a finite quasi-simple group, which is not too small, so S modulo its center should have size at least C. And if we choose M automorphisms, beta 1, beta M, and choose M divisors of Q. So we've got automorphisms of the group, and we've got some positive integers. So beta 1 up to beta M are automorphisms of S, and Q1 up to Qm are divisors of Q. Then every element of S can be written as a product of commutators. S commuted with alpha 1, beta 1 to the Q1 dot 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 S alpha M beta M to the Qm. So that means it's a product of commutators of an element of S with a suitable power of a certain automorphism. And what are the betas? The betas are given, and the alphas are adjustments for inner automorphisms. So this, of course, is proved by examining the finite simple groups. It's not easy. I mean, I don't think an expert on finite simple groups would say, yes, that's obvious. On the other hand, you would have a rough idea how one would approach it. You have to examine the simple groups. You have to look at the action of automorphisms on the root subgroups and then solve equations over finite fields. It's quite complicated. So, as I say, to go from that one to that one is a long, difficult combinatorial argument. You end up having to solve equations in a group, because you could say you're trying to solve an equation here. Some element of this is a product of f qth powers. So you're solving an equation, h equals x1 to the q dot 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 xf to the q. So you do a Hensel's lemma type approach. You say you have a solution modulo some small normal subgroup. There's an error term in the normal subgroup. You want to kill the error term. You kill it by adjusting the x's, and you end up having to solve equations in the normal subgroup. So the normal subgroup might be a small nilpotent group, or it might be a semi-simple group, and then one uses different methods. Anyway, I've stopped there, but I hope I've given you some idea of why we like the classification. Thank you.
Thank you very much. Are there questions, comments? That's not the case. Then let's thank the speaker again.